Hi everybody, welcome to Math 30-2. We're going to be starting the probability unit today. And so take some time, get your calculator, get your paper, take some notes, and let's get started. So first of all, probability as a definition is the likelihood that an event will occur. And sometimes we've heard it talk about the chance or prediction. Now, probability of an event is a number, and it's a number between 0 and 1. Where 0 is the probability that the event will not occur for sure, not going to happen. So there's 0 chance of something happening. We say the probability of that event is 0. Well, on the other extreme, we have the probability or the event is going to happen for sure. And that has a probability equal to 1. Now we have a formula for the probability of an event. And that's the number of favorable outcomes, so in the numerator, divided by the number of possible outcomes in the denominator. And we see this a lot. We talk about flipping a coin, heads or tails, where if we called heads, that means the probability of the number of favorable outcomes would be the head. So we would write it 1 over the probability of the total number of outcomes. Well, there's only 2 when we flip a coin, so it would be 2. So we could write it as this fraction, or we can convert the fraction to a decimal. Now, there's 2 types of probabilities. There's what's called the theoretical probability, and that's what we do in theory. It's the theoretical definition by that formula here. For example, in the roll of a die that has 6 sides, what is the probability of getting an even number? Well, when we look at the total possible outcomes of rolling a 6-sided die, we know we have the numbers 1, 2, 3, 4, 5, and 6. So there's 6 possibilities. Well, what are the even numbers? Well, we have 2, 4, and 6. So there is 3 favorable outcomes, and there are 6 possible outcomes. So as a fraction, it's 3 over 6, but we like to sometimes reduce our fractions by dividing the top and bottom by a common factor, in this case 3. So we get 1/2, and if you want, we can put it as a decimal. Now this differs from the experimental probability. This is based on repetitions of an actual experiment. Therefore, it is what we actually counted. Because remember, the experiment may not be exactly the theoretical. For instance, if we tossed a coin 10 times, but we got 8 tails, well, then the experimental probability of getting tails would be 8 over 10, or as we reduce it down, that would be divide both sides by 2, 4 over 5, which as a decimal is 0.8. So we have a probability of 4/5 or 0.8, which is different than what we know from above here of getting heads or tails, which was 0.5. Now let's look at the complement of an event. This is the probability that an event will not happen. And we have a special way of writing it. We say P of E, just like we normally would, the probability of event E, but we put this little bar over the top. And this represents the probability of the complement. Now, in our Venn type diagram right here, if A is our event, then A bar is our complement of that event. And because these are both within the universal and there's nothing else that can happen, within this, it's either A or not A in this case, the probability of A plus the probability of the complement of A has to equal 1. And we can rearrange this just like any formula, where the probability of the complement of A must equal 1 minus the probability of A. Now let's think about that. Think about a coin toss. Well, we know the probability of getting heads equals 0.5. Well, by our definition, what is the complement of heads? Well, the complement of heads is tails. So the probability of tails, by definition, would be 1 minus the probability of heads. Let's just write it as the formula first. And then substituting it in, we get 1 minus 0.15, which is 0.5, which we knew anyways. But just to show the example of what the complement probabilities would look like. Now, the next definition is sample space. Now, the sample space is the set of all possible outcomes. So, for instance, and we often use tree diagrams to help us build the sample spaces. For example, here we have the sample spaces of coins, a toss. Well, we know it's a head or a tail. And then we have the sample space of a die, which is singular for dice, by the way. And there are 6 outcomes, and namely, they're 1, 2, 3, 4, 5, and 6. So let's look at an example to illustrate this. Let's say we are going to toss a coin and roll a 4-sided die. And it's asking us to determine the sample space. Well, let's use a tree diagram. Well, when we toss a coin, we have 2 outcomes. We have a head and we have a tail. Well, let's say we got the head first, and then we're going to roll this 4-sided die. Well, there's 4 possible outcomes when we roll the die. We have 1, 2, 3, and 4. But what if we have a tail? Well, we still have 4 possible outcomes. 1, 2, 3, and 4. So in the sample space of tossing a coin and rolling a 4-sided die, we can get a head and then the number 1. We can get head and number 2, and so forth and so on. And we're just going to write those all out. And then we can switch over to the tail. So the tree diagram helps us to figure all of these out. And while it's not as complex for these smaller tree diagrams, sometimes when we have more than 2 events, it helps us really visualize these things. Now, in this sample space, we have 8 outcomes. And we're going to use that to help us figure out the probability of the following. The first one being, what is the probability of getting heads or 2s, or head and a 2? Well, in this case here, there is only one event with a head and a 2, and it's this one right here. So there is one possibility with 8 outcomes. So our probability is 1 over 8. The next one is the probability of t with an even number. Well, there are 4 t's, but there's only 2 that have even numbers. That's t2 and t4. So there are 2 events that have the t and an even number out of the 8, or in other words, 1 over 4. Now the next one has, what is the probability of getting H3 or T4? Well, there is H3 and T4. There are 2 outcomes that satisfy this or that. In other words, H3 or T4. And there's still 8 outcomes in total. So we have 1 over 4. The last one is, what is the probability of H7? Well, there is no H7 out of those 8 outcomes, so the probability of this is 0. Let's go on to number 2 here. It says, draw a tree diagram for 3 coins and list the sample space. Now, when we have these multiple events, we start with the first event, which is H or T. That's our 2 options. Well, we're going to toss the coin, another coin, and that one has an H or T. Well, what if it was a tails the first one? Well, same thing. Even if we got a tail, oops, we have H or T here. And then what about the third? Probably getting the idea here. Each one of these can also have an H or T coming off each one of the possible outcomes in the second coin toss. So what is the sample space? Well, the first branch, and when I say branch, I mean this one right here, that gives us H, H, H. The second one gives us H, H, and then T. The third one comes here and then goes up like that. So it gives us H, T, H, and so forth and so on. And then it starts with the T, H, H, and then the T, H, T, and the T, T, H, and finally the T, T, T. So in this one, we still have 8 outcomes, even though there were 3 events. So example 3, let's look at number 3. List the sample space for each of the following and answer the questions that follow. Well, here, they've actually already done it for us for part A. For instance, here, if this is our first die, and this represents the second die, all of these things in here represent the possible outcomes of rolling each. So the first number represents the first, and the second represents the second. Now, what they've done over here is they've created another table that represents the sum or adding all the numbers together that on any dice rolls. For instance, if we get 1 and 1 on the die, the sum of those two is 2. Or if we get 5 and 4, the sum of those two are 9. So they filled this table out for us. So let's look at what our probabilities are asking. What are the probabilities of rolling doubles? Now, doubles means getting 2 of the same type. Well, in this one, all of these here down the diagonal represent getting doubles. And if we count them up, we know that there's 6 of them. Well, the total number of outcomes in here is 6 by 6, or 6 times 6, which is 36. So there's 36 little squares in there. You don't have to add them all up one by one. We just know that there's 6 in the horizontal and there's 6 in the vertical, so we can say 6 times 6. This must be reduced, so we get 1 over 6. So let's look at the probability of rolling a 2 and then a 3. Well, remember here, this line here represents having a 2 for the first one. These are the 2s. And then the 3 for the second die is this one right here. So there is only one option where we roll a 2 with the first die and then a 3 out of all the 36 options right here. So we roll the 1 first, or sorry, the 2, then the 3, and there's only one outcome where the 2 is from the first die and the 3 is from the second die. Number 3, what is the probability of rolling a sum of 9? Well, now we have to go to the other table. Now, all along this diagonal here, this is where the sums equal 9, and there's 4 of those. But there's still 36 outcomes, and we're going to reduce our fraction by dividing top and bottom by 4, and that's going to give us 1 over 9. Number 4 is, what is the probability of the complement of rolling a sum of 9? Well, the complement of rolling 9 is the complement, or is not 9. What is not rolling 9? Well, we can do this using our little formula. The probability of the complement of 9 equals 1 minus the probability of 9. Well, now that we've figured this out from part 3, we can just say 1 minus 1 over 9. I'm working in fractions just to get us used to working in fractions. I'm converting my 1 to 9 over 9. So we have that common denominator, and that gives us 8 over 9, which makes sense because we have 1 over here, 8 over here, and they have to add together to be the total of 9. The next one is, what is the probability of rolling a sum of 3 or a sum of 4? Well, how many events are included in this? Well, for 3, we have 2 events right here. And for 4, we have 3 more. So in total here, the probability of the sum of 3 or sum of 4 is 5 favorable events over the total number of total outcomes, which is 36, which is 5 over 36, and we can't reduce this any further. And the last one here is 6. What is the probability of rolling even numbers? Now, I am interpreting this as where neither one of the die has odd numbers in it. So in this case, the probability of even numbers, let's just erase some of this stuff here, just to clear it up for us a little bit. So rolling even numbers, for instance, nothing in the first row right here has both even numbers, but in the second row, this one, and this one, and this one. And notice this will only happen in every second row because all the other ones have odd numbers in them. So for this one, the total favorable outcome is 9 over the total outcomes, which is 36. And we can reduce this down by dividing both by 9, which is 1 over 4. Let's look at number 4. It's saying complete the tree diagram for a family of 3 children. So in other words, the first one is a boy or a girl. The second one must be a boy or a girl. But then here we also have boy, girl, boy, girl. So for the third event, notice our tree gets a little tight here, but don't worry about it. So what is the sample space? Well, let's write those out. We can have 3 boys. We can have first 2 are boys and the last one's a girl. Then we can have first boy, boy, and boy, girl, girl. Keep going. Oh, I noticed. Ignore that. There we go. And then girl, boy, boy, and girl, boy, girl. All the way down to the bottom of 3 girls. So the first thing we figure out is how many outcomes there are. Well, there's 8 possible outcomes. And the first question, what if is the probability of all boys? Well, there's only one event that has all boys, so one outcome. So the probability of that would be 1 over 8. What is the probability of all boys or all girls? Well, that one's a little different. We have to add the second outcome there. So that would be 2 over 8, but we don't want to leave it like that. We want to put it into reduced form, which is 1/4. What is the probability of exactly 2 boys? Well, we have to look for all the outcomes that have exactly 2. That does not include this one because it has more than 2, so that's going to include that one. 2, 3, and that would be it right there. So we have 3 outcomes that have exactly 2 boys. And this one can't be reduced any further. Then the last one is at least 1 girl. Well, if it's at least 1 girl, it can have 1 girl, it can have 2 girls, or 3 girls. So the only one that does not have any girls in it is this one right here. So we can actually look at this as the probability of 1 minus the probability of all boys, because that gets rid of all the other ones. It doesn't get rid of them, sorry. It makes our little calculation a little easier. We can just say 8 over 8 minus 1 over 8, which equals 7 over 8. So we could have counted them or done it this way as well. So number 5. A spinner is labeled with 3 colors, red, green, and blue. Marcus spun the spinner once and then tossed a coin once. It's asking us to draw a tree diagram and list all the possible outcomes. So the tree diagram, we're just going to use R for red, green, and blue. And then we have a coin toss of heads or tails. So we can have red or H, RT, GH, GT, BH, or BT. Now part B is asking, what is the probability of getting blue on the spinner and head on the coin? Well, we go down to the bottom here. There's only one outcome, one favorable outcome, which is 1, over the total outcomes, which in this case is 6. So our probability is 1 over 6. The probability for C of red or green on the spinner. So red or green on the spinner means we're going to be looking at least at these here. But it's asking for a tail on the coin. So that's going to eliminate this one and this one. So now we only have 2 outcomes where there's a green or a red on the spinner and a tail on the coin. So that's 2 over 6, but we like to reduce that down to 1 over 3. So let's look at example number 6. A box contains 36 red chips, 24 blue chips, and 40 green chips. If you take a chip from the box, what is the probability that it will be a red chip? Well, the first thing we need to know before we figure this out is what are the total number of chips? Well, if we have 36 plus 24 plus 40, that equals 100. So our total number of outcomes is 100. Well, what is the probability of getting a red chip? Well, that's going to be 36 over 100. Now let's reduce that down. They're both even numbers. In particular, they're divisible by 4. So we have 36 divided by 4 is 9, and 100 divided by 4 is 25. So B, what is the probability that it is not a red chip? Well, we can go and either count up the blues and greens and form the fraction that way, or we can use our definition of the complement, where we can say it's going to be the probability of not red equals the probability of 1 minus the probability of red, which we've already figured out. And we can figure that's going to be 1 minus 9 over 25. Just fixing that up there to make a common denominator. And 25 minus 9 is 16 over 25. So we have 16 over 25. Part C, what is the probability that it is not a green chip? Well, not a green chip, that it's blue or red. So we can look at it this way without discussing the complement. We can say, what is the probability of blue or red? And we can just add the blues and reds together. Well, the blue, there's 24. The red, there's 36. So we have 24 plus 36 right there. We have 60 over 100. And that equals 6 over 10. But we want that to be reduced. So we're going to divide top and bottom by 2, which gives us 3/5. For part D, what is the probability that we do not have a red chip or not a green chip? Well, if it's not red and it's not green, it has to be blue. So we have 24 over 100. And reducing that down, we can divide both things by 4, which is 6 over 25. Let's move on to number 7, where we have 3 unbiased coins. You're going to see that a lot, by the way. Unbiased just means that it's a fair coin, that the probability of tossing a head or tossing a tail is equal. So it says, what is the probability of getting at most 2 heads? Well, let's start with our tree diagram here, where we have head or tail is our first option here. And then we build it like this. So building out our sample space, we can have the 3 the same, and we can just continue down, filling this out. And then the last one is they're all tails. So what is the probability of getting 2 heads? So the probability of at most 2. Well, let's figure out which ones they are. Well, this one has 3, and it can't be 3 because it's at most 2. So it can't be that one. This has 2. This has 2. This has 1. This has 2. This has 1. This has 1, and this has none. But that is still counts as at most 2, because it can be probability of at most 2 heads is really the probability of 0 plus the probability of 1 plus the probability of 2. So we can really look at it as either 3 single probabilities like this, where there is 1 over the 8 plus 1 head. Well, there was 1, 2, 3 that had 1 head. And there were 1, 2, 3 that had the 2. So we can do these as single probabilities, or if you want, you can just kind of count them up in your head like we did here, meaning we can see that there's 7 off to the side. So we have 7 over 8. Let's move on. Now, in probability, we talk about a standard deck of cards. Now, a standard deck of cards has 52 cards in it, and they are 2 different colors. There's 26 red cards and 26 black cards. Now, there's what's called face cards. Now, the face cards, there are 3 different ones. There's a jack, king, and queen. And so there's one of what we call suits. And there are 4 types of suits, and it's clubs. Club is a black card. We can write that down just to remind us. As is the spade. The spade is the black card right here. Then we have hearts and diamonds, and those are the red cards. So we often use these to do some probability questions like number 8. A card is drawn from a well-shuffled deck. What is the probability that the card will be a heart? Well, the favorable outcome is heart, and there's 13 hearts in a deck, and there are 52 cards in a suit, with the total number being 52. Now this actually can be reduced down, because 13 times 4 is 52, so we have 1 over 4. Now what about the next one here? A black card. Well, there are 26 black cards in the deck. That's the clubs and the spades. And we have 52 still as our total outcomes. So this now is 1/2. What about a red 5? Oh, now we've really kind of narrowed things down. Now, there are 2 red suits that are the hearts and the diamonds. And in each of these actually, without including the jack, king, and queen, they run from what's called an ace all the way up to 9. Okay, just so you know, we put those in. And it's not only the hearts, it's the diamonds, the spades, and the club. But we don't have a 10. So it goes ace, 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, how many red 5s are there? Well, there's a 5 of hearts and a 5 of diamonds. So there's only 2. And there's still 52. So we do reduce this down, divide both by 2, and that's 1 over 26. What about a black jack? Well, again, although there's 4 jacks, 2 of them are black. They're the club and the spade. So again, we have 2 over 52, which is still 1 over 26. What about a face card? Well, as we mentioned, there are jack, king, and queen. Those are the face cards. And there are 4 each. So in total, there are 12 face cards out of 52. Now, this one, we have to divide each of these by 4. So 12 divided by 4 is 3. 52 divided by 4 is 13. Now, what about the probability that we draw not a face card? Well, we can look at this by saying 1 minus the 3 over 13, which it equals 10 over 13, because that's the complement of E. So not a face card is the complement of that one. So we say 1 minus 3 over 13, which is 13 minus 3 with the common denominator of 13, which is 10 over 13, and we can't reduce that any further. Let's look at number 9. Now, this one is asking us what is the least likely to occur? In other words, which has the smallest probability. So in order to determine these, let's look at this for this spinner. It has numbers 1 through 6. We give it a spin. And the first question is asking, what about if it's an odd number? Well, there are 3 odd numbers. And if you put that in this, we can have an outcome of 1, 3, or 5. That would be, what is the probability of a 1, 3, or 5, basically is what we're saying. So the probability of an odd number is 3 over 6, but we're going to reduce that down to 1/2. Now the next one is a prime number. Now remember, a prime number is a number that only has 2 factors, 1 and itself. And in this case, the prime numbers are 1, 2, 3, 4 is not a prime number, 5, and 6 is not a prime number. So there are 4. So the probability of prime is 4 over 6, which is 2/3. Now, what is the probability that the number is a perfect square? Now, remember, perfect squares are those that can be written like 2 squared, 3 squared, 4 squared, and so forth. So in this case, the first 3 perfect square numbers are 4, 9, and 16. So the only one that's a perfect square is 4. So the probability of the perfect square equals, we're going to say 1 over 6, and then we're done. And what about the probability that the number is divisible by 2? Now, what they mean here, divisible by 2, well, they're all divisible by 2, but only 2 of them end up with a nice number at the end, a nice even, like, whole number. That's what they actually mean there. So the probability of, divisible by 2 equals, well, there's only 2 numbers. It's the 2 and the 4 over total probability of 6, or outcome, sorry, and that gives us 1/3. But the question is asking which it is least likely to occur. Now, it's harder to compare probabilities when they have different bases, like 1/2, 2/3, 1/6, 1/3. So we're going to look at the numbers that have the 6 as the base, because of course, whichever has the smallest numerator is going to have the smallest probability. And that would be the probability of the perfect square, because it has a probability of 1/6 where the others are 2 or higher. So the probability of the perfect square is the least likely to occur. Oops. Okay, let's go on to 10. Now we are back to our Venn diagrams, where there are 28 students in Mr. Connolly's grade 12 math class. The number of students in the yearbook club and the number of students on a student council are shown in the Venn diagram. Use the diagram to answer the following questions. So let's kind of look over here and just remind ourselves about the parts of the Venn diagram. Well, we know that the middle piece right here, this is the intersection, which is Y intersect S. And sometimes we say this means that they are doing Y and S. So that is the yearbook club and the student council. So there are 2 people who do both. There are 5 people who are only in the yearbook, and there is 1 person who is only in student council. That must mean there's a bunch of people who are not in any of them, who live in this outside region right here. And to figure those out, we just got to take the total number of people in the class, which is 28, and subtract 5, 6, 7, 8. So the number of people who do not do any are 20. So there's 20 people outside of those right there. So the first question is, what is the probability of being on the yearbook club and on the student council? So the person that we pick, basically is we're saying, what is the probability of Y and S? Well, there's 2 people there, and there's 28 people in the class. So the probability of that is 1/14. The next, what is the probability of Y intersect with the complement of S? Well, if this part here is a complement of S, let me just get my shading out. So the complement of S is everything outside S right here. And we're just going to shade in everything right here. There we go. Oops, almost forgot this spot. Oops. I was never good at coloring. So this is the complement of S. Now, it says the intersection of the complement of S and Y. So let's color in our Y. Now, the intersection is the overlap of S and Y in the complement. So that means it's this moon-shaped, crescent moon-shaped here. So that means there are 5 people in that intersection. So in other words, the probability of Y intersecting with S prime equals 5/28. Now this one here, we can't simplify any further. So we have 5/28 right here. The next one is, what is the probability that a student is in the yearbook club? Okay, so we pick a student. What is the probability of Y?
Well, that means the probability is these 7 students right here. Even though 2 of them are also on a S, they're still on the yearbook club. So we have 7 over 28 right here. Now this one actually can be reduced down a little bit here because we can divide top and bottom by 7 to get 1 over 4. And the last one, what is the probability that they are in neither club? Well, that is those things that are outside the union of Y and S. Remember, the union is this part. Let me get my highlighter out again. Let's do it in purple. This is the union, this part here and this part here, and everything outside of that. So now what we appear to be pink right now, that is all of those guys there, and the probability of neither club, so we can write it as Y union S, and we can make that the complement of that. That equals 20 over 28. And if we want to divide both sides by 4, or sorry, not both sides, numerator, denominator by 4, we get 5 over 7. Let's go to the last one here. Whoops. Now this one here is a 3 Venn diagram. Remember, when we do these, we want to read the question first. And often they'll give us information either where we can start in the middle and expand out, or we're given enough information on what's on the outside and we can expand in. This one's going to be starting at the middle. Sammy asked 15 people which drinks they liked from tea, coffee, and milk. All 50 people liked at least one. Now that's important because that tells us there's nobody going to be outside these 3 circles. So there's going to be nobody in this region here. They say that 19 people like all 3 drinks. 16 people like tea and coffee, but not milk. 21 people like coffee and milk. 24 people like tea and milk. 40 people like coffee. 1 person likes only milk. And Sammy selects 1 person at random from the group of 50 people. And it's asking us, first of all, to find what is the probability that a person likes likes coffee or tea, but not milk. Well, we need to fill this in first. So, like I mentioned, we have 19 people who like all 3. So we can put 19 right here. Now, 16 people like tea and coffee. Now, tea and coffee, that would be an intersection of that, which would be this part right here. But we're not including the people who like milk. So in other words, that 16 is this part here, this top piece, because the 19 include the people who like all 3. And so, in other words, only like tea and coffee, but not milk, would be the 16 here. 21 people like coffee and milk. Okay, so coffee and milk would be this intersection piece down here. But now 19 are already included in the intersection of all 3. So to figure out what goes in this section right here, we actually have to subtract 19 from 21. So 21 minus 19, which is going to equal 2. So 2 people are going to be in here. Now, the next one is 24 people like tea and milk. Now we're coming back over here. So tea and milk is this whole intersection here, but we've already included 19 of those. So we have to say 24 minus tea and milk people, which is, tea, milk, and coffee people, which are the 19. So that means 5 go into this region here. And notice how these 2, this one and this one, were different than the first one where we were already given that it did not include the milk, so we didn't have to do any subtraction, whereas these we did. Now it says 40 people like coffee. Okay, the 40 people who like coffee. So that means this coffee circle right here has to equal 40. Now we already have 16, 19, and 2. So really what we're doing, we have to say 40 minus 16
19, and 2, and that's going to give us that only coffee region, and that gives us 3. So that means 3 people like only coffee but not tea or milk. And then we say 1 person only likes milk. Great. This is the only likes milk region, so we don't have to do anything there. And we only have 1 region that we don't know, and that is the only tea region. So what we actually have to do is we have to add up all of those numbers within the other 2 circles, and that also overlap a little bit into the tea. So 16, 19, 5, 3, 2, and 1. Those all add up to 46. So we're going to take the total, subtract 46, and that is going to give us the only tea, guys, and that is 4. So now we have all of our information that we can actually answer. What is the probability that a person likes tea or coffee but not milk? Well, there are 16 people in that, so we can say 16 over 50. So that's the probability of coffee, tea, or milk, but not milk. I'm getting a little squished. My pen's slowing down. Equals. And what do we got here? Well, that is divisible both by 2, so we get 8 over 25, and that can't be reduced any further. What about the next one? The next one is, what is the probability that a person likes coffee and tea? Well, the coffee and tea folks live right here. So that means the probability of basically the intersection of coffee and tea, that equals 16 plus 19. That's going to be our numerator, all over the 50 people in class or who are surveyed. And that's going to give us 35 over 50. And we get 35 over 50 here. That's going to give us, dividing both sides by, or sorry, not both sides, numerator and denominator by 5. That's going to give us 7 over 10. And if we want to write it as a decimal, which we haven't done very much this video, it can be written as 0.7 to 1 decimal place. Well, that's the end of this video. If you have any questions about this, don't hesitate to get in touch. Hope you have a great rest of your day. Take care.